And if you are joining us in person, English or Korean translations are available. For those of you who are joining us online, you can select between the English and Korean audio feeds. Welcome everybody to this great event.
IBS의 개원 10주년을 축하드립니다.
We wish you all the best for your next 10 years. Joyeux anniversaire!
Congratulations on the 10th anniversary of the founding of the Institute for Basic Science.
My heartfelt congratulations and those of the Max Planck Society on the wonderful 10th anniversary.
앞으로도 IBS가 세계적인 기초과학 연구기관으로 지속 성장할 수 있도록 관심과 애정을 가지고 응원하겠습니다.
Good morning, everybody. Welcome to today's program. It's my great pleasure to welcome everybody to today's lecture by Dr. Robert Lefkowitz. My name is Orlando Scher. I'm the Associate Director of the IBS Center for Genomic Integrity. Thank you, everybody, for was able to join us live, and we also come to you by Zoom and on YouTube. We're conducting today's event in a hybrid format, as one has to do in these days. We have long hoped to overcome the pandemic and go back to all in-person programming, but as you all know, this is difficult, but we do our very best to keep going with our research and doing our discoveries. And we want to thank, of course, all the frontline workers and medical staff to keep us safe in these difficult times. We do our best to comply with the protocols as we do now, so thank you for your consideration. For one of our many 10-year anniversary events of the IBS, today we have several world-leading scientists as panelists, and we warmly welcome you to this event. Joining us today, we're very pleased to announce, is Dr. Robert Lefkowitz, the 2012 Nobel Laureate in Chemistry and Professor of Duke University. Thank you for joining us today, Dr. Lefkowitz. How are you?
I'm fine. Thank you very much for the greeting.
Okay, great to have you here. Thank you for being with us. We also have President Pangil Shu of the Korea Brain Research Institute, Director Hee-jung Choi of Seoul National University, and Director Kyung-jae Myung of the IBS Center for Genomic Integrity. We will begin with the introduction of today's speakers, Dr. Lefkowitz by Director Myung. Then we'll have a panel discussion on the research pioneered by Dr. Lefkowitz, and also in more general terms, what it means to be a scientist, what motivates scientists to do what they do. We will accept then after the panel discussion both online or in-person and offline discussions. And if anybody has a question in the audience, please raise your hands and we'll bring the microphone to you. And for those of you who are online, you can submit your questions by entering them into the chat box. Also joining us today are students and researchers from IBS, university and research institutes. We see many of them on screen through Zoom, and our attendance here is unfortunately limited through 100, but we appreciate that we can interact with many more of you online. And now I ask Director Kyung-jae Myung to introduce our speaker, Professor Lefkowitz. KJ, please.
Okay, thank you, Orlando. It's my great honor to introduce today's speaker, Dr. Robert Lefkowitz. So he actually was born in New York and then grew up, and as you can see, that very famous Bronx High School. And then he did his BA and MD degree in Columbia University. And then he did his clinical and research associate in National Institute of Health, and where I was actually a few years ago. And then in 1973, he started his career in Duke University. And since then, he stayed there for a long time, and then until now. And he became a Howard Hughes Medical Institute researchers since 1976. He has been really successful scientific career, and that's one of the best, like IBS, in the United States. He got so many awards, so I just listed many of them. And Nobel Prize, we all know already. And in addition to that, he got the Research Achievement Award from American Heart Association and National Medal of Science and Shaw Prize in Life Science and Medicine. And you can look at that, and probably there might be more than I just found in the internet. So what he has done to the field, he has been focusing on one thing. It's called the G protein coupled receptor. I got this, the picture from the Campbell Biology in Focus. That's a general biology textbook for most of the university. And that much, this is a very important thing. He found this G protein coupled receptor, cloned it, and then purify it, and then prove it. This is indeed regulate everything. And he will probably tell you, probably more than 30 to 40% of all the drugs that we are currently using are targeting this G protein coupled receptor. So he is a great scientist, but in addition, he's a good writer. He recently published this book, and a funny thing happened on the way to Stockholm. And he started to sell it, and this is actually, I got from Amazon, the custom review, 4.7 out of 5 in 120 global rating. And you can see wonderful contribution, thoroughly enjoyable read, excellent contribution. And these are all the comments by all the readers who read this book. So without further ado, it's a great honor to introduce Bob Lefkowitz. Bob?
Thank you so very much for that very kind introduction.
Okay.
Very much appreciated.
Let's welcome Bob with a great applause.
So thank you very much for that kind introduction. As you can see, I've titled my talk for tonight, A Tale of Two Callings. Now, a calling generally refers to something that we tend to associate with clergy, like priests or such. It's sort of a sense that you were destined to do a certain thing. But you can feel a calling to any vocation or avocation, not simply to the religious calling. And I've been remarkably fortunate in my career in that I have felt a calling twice, initially to the practice of medicine and subsequently to the scientific life. So let me tell you how I came to these two callings and how they have formed and directed and influenced my professional career. As I said, my first calling was to the practice of medicine. And I associate that, oh, having trouble advancing my slides here. Okay, there we go. I really attribute that initial calling completely to this man, Dr. Joseph Feibusch. He was a general practitioner of medicine in the Bronx, New York City, when I was growing up there in the 1940s and 50s. And I was totally taken with this guy. He would come to the house when I or a family member was ill, and he would bring that black bag with him, from which he would produce all manner of magical instruments like a stethoscope, an otoscope, a reflex hammer, all sorts of things. And I just thought this was the greatest thing. He would lay on hands, he would let me play with these instruments. And so I was convinced really from a very young age, as shown here, probably about age 6 or 7, that I wanted nothing in life other than to be someday like Dr. Feibusch and be a practicing doctor. And so I set my mind to that with tremendous focus. I attended a special high school for gifted and talented students in New York City. And I stress this was a public school. The only criterion for admission was your score on a competitive examination. So they took in only the best and the brightest students. From there on to Columbia College, as you heard, where I majored in chemistry, and then to medical school at Columbia College of Physicians and Surgeons, shown here in 1966 at my graduation from medical school with my parents. I want to emphasize that to this point in my career, I had never done any research. Whenever there was an opportunity to do a research elective in medical school, I opted for a clinical elective so that I could hone my clinical skills. I loved science. I was very interested in science, but I seemed at this stage to have absolutely no interest in being a scientist myself. My dad, shown here, would die 2 years later of his 4th heart attack, his 4th myocardial infarction at the relatively young age of 63. My mother also had a heart attack in her 50s, and from the two of them, alas, I inherited genes for coronary artery disease myself. And I have little doubt that my parents' medical history had much to do with my initial choice of cardiovascular disease as a specialty. I stayed at Columbia for my internship and residency, shown here as a medical intern, and would have gladly gone on to finish my clinical training and then spend my life in the practice of medicine. But that was not to be, because my career, as the careers of really all other physicians and many other young men at that time, was interrupted by a cataclysmic event, what we in the United States refer to as the Vietnam War. This was an extremely unpopular war. There were demonstrations, even riots against this war, which was felt by many of us to be at least immoral, if not illegal. And we didn't want to serve. However, we had no choice because there was a doctor draft during the Vietnam War. So this meant that following their internship or a period of residency training, doctors were inducted for 2 years of service in the armed forces, potentially disrupting their plans to begin clinical residency or continued education and training toward a research career. There were no exceptions. you were drafted into either the Army, the Navy, the Air Force, or the United States Public Health Service. And if you were drafted into any of the first three, you were pretty much assured that you would spend one of your 2 conscripted years in Vietnam, which none of us wanted to do. So it made the United States Public Health Service by far the most popular service for physicians, because many of their assignments were in the United States, and some were even at research institutions like the NIH and the Communicable Disease Center. As a result, the competition to gain commissions as an officer in the Commissioned Corps of the Public Health Service was intense, and only the most successful students with the best recommendations could get those commissions. However, I was successful and was able to gain a commission in the Public Health Service as a lieutenant commander. Was assigned for 2 years to the NIH, where I went in 1968. This is a picture of my group at the NIH. That's me in the autumn of 1968. Here at the NIH, I spent about 20% of my time taking care of patients who had been admitted to take part in clinical research studies, and the other 80% of my time learning how to do research in the laboratories of 2 mentors. And here at the NIH, I encountered something that I had never encountered before up to that point in my young life: failure. Protracted, unmitigated failure. For a year or a year and a half, I struggled in the laboratory and made no headway with my project. I think I became clinically depressed. My mentors did everything they could to keep my emotions and spirits up, but I was very down. And so after about a year, I realized that research could play no role in my future career. And so I made plans that after another year, filling out my commitment of 2 years, I would travel to Boston, to Harvard, and finish my clinical training at the Massachusetts General Hospital, the Harvard Teaching Hospital. As luck would have it, during the final 6 months of my time at the NIH, my project began to work. I began to enjoy it. I published my very first handful of papers and really got a taste for the first time of what it felt to be somewhat successful in research. However, this was certainly not enough to convince me that I should be doing any research in the future. And so off I went to Boston to find the next phase of my career. Before leaving the time at the NIH, I want to make another point, which was, I told you just how elite the group of us who were drafted and sent to the NIH was, just because of the intense competition. Remarkably, between 1964 and 1972, 8 years, the peak years of the Vietnam War, during which perhaps 50 to 100 of us were assigned to the NIH through the Public Health Service each year. All young physicians with essentially no training in research. Of that group, in 8 years, 10 of us, 10, would go on to win the Nobel Prize. Their names are shown here in this yellow ribbon and are colored blue. Now, this is a remarkable record, to say the least. But what is equally remarkable is to look what's above in this area of this chart. So this is a family tree of these 10 Nobel laureates, showing essentially their scientific parents, grandparents, and then great-great-grandparents, etc., back many generations. Every name colored blue is a Nobel laureate. Now, what you can see is that for 4 of these 10 Nobel laureates, they actually trained with a Nobel laureate. And for the other 6 of us, you don't have to go any further back than a scientific grandparent to find a Nobel laureate. And if you go back even further, you can see that some of these lineages have Nobel laureates in absolutely every generation. Moreover, if you go back several generations, you can find that even though we were all biomedical scientists, our scientific great-great-grandparents were often Nobel Prize-winning physicists like Chadwick, Schrodinger, Bohr, Pauling. So what's the point? I think the point this shows that if you put together extremely bright and motivated young aspiring scientists and physicians together with absolutely outstanding mentors, good things can happen. And I'll say a little bit more about my ideas about mentoring in just a few minutes. This shows me at the Massachusetts General Hospital in the fall of 1973, where I threw myself into full-time clinical work again. And I enjoyed it. I was always very good at clinical medicine, and that had been my first love. And so for 6 months, I followed an exhausting schedule. But then over the holiday season, after these 6 months, I found myself musing over the fact that although I was enjoying the clinical work, as I always had, something seemed to be missing. I didn't feel completely fulfilled. And it was then that I really had my epiphany and experienced my second calling and realized that what I was truly missing was being in the laboratory day to day, to having data every day, to being challenged by having to design experiments, analyze them, and wrestle with difficult problems. And so I took the decision to go back into the laboratory part-time. And so for the remaining 2.5 years that I was in Boston, I split my time between finishing my clinical training in medicine and cardiology, but also working in the laboratory of a new mentor. And then in July of 1973, I got a nice offer to go to Duke, which I did. And as you heard, I've been there now approaching 50 years, but not quite. And I split my time between doing clinical work, teaching medical students and residents clinical medicine, and also setting up and running my laboratory program, shown here with one of my postdoctoral fellows. When I first came to Duke, for the first couple of years, I probably spent about 60% of my time in the laboratory and 40% in the clinics. But as my laboratory program took off and we began making discoveries, I was drawn deeper and deeper into the laboratory. And before I knew it, I was spending 80 or 85% of my time in the lab, and perhaps only about 15 or 20% in the clinics. That division of labor persisted for many years, but then I finally, about 15 years ago, hung up my stethoscope for good and have been in the laboratory full-time ever since. Now, I'm not going to speak during this talk about my scientific research career in terms of the specifics. If you want to ask questions, we can talk about it. But, we've published lots of papers. And as you heard, we discovered this G protein coupled receptor family. When I began my work in the late 60s and early 70s, there really was no general consensus that there was even such a thing as a receptor. Neither pharmacologists nor biochemists really believed in them. For example, this is taken from Earl Sutherland's Nobel lecture in 1971. He had won the prize for discovering the enzyme adenylate cyclase, which makes cyclic AMP the second messenger, which diffuses into the cell, activates protein kinases, and leads to physiological responses. You can see that for Sutherland, there really was no such thing as a receptor. He imagined that the receptor, if one wanted to even use that term, was the actual enzyme adenylate cyclase. No receptor, no G protein. None of that had been discovered yet. Our contributions over many years, as you heard, focused on discovering this remarkable and huge family of receptors, which we now call G protein coupled receptors because their signal transduction occurs through the so-called heterotrimeric G proteins. And when we cloned the first dozen or so members of the family, we realized that they had this very conserved 7-membrane spanning domain architecture, which was shared with a wide variety of other receptors. For example, rhodopsin, the visual pigment, which is essentially a receptor, a G protein coupled receptor for photons of light. There are anywhere from 800 to 1,000 different types of these receptors in humans, and they regulate virtually all known physiological processes in human biology. And that includes not just neurotransmitter and hormone receptors, but also a variety of sensory receptors, such as those for taste and smell, and as I mentioned, vision. As was just mentioned, today, this G protein coupled receptor family is by far the largest family of drug targets. In fact, as you heard, at least 30% of all drugs in clinical use today are target one or another of the G protein coupled receptors. This amounts to over 700 drugs. So even though our research was always carried out at a very basic or fundamental level, the implications of the work for clinical medicine and practice have been very substantial. I think that's a point to underline, that you don't have to do clinical or even translational research to make discoveries that can powerfully impact the practice of medicine. Now, I mentioned the importance of mentoring before, and how important mentors were in my early career. I want to now share with you some of the things that I've learned about mentoring in my long career. About 250 scientists have trained in my laboratory, mostly postdoctoral fellows of one kind or another, but several dozen graduate students. That number does not include many dozens of undergraduates who have also worked in my lab. So what are some of the principles of mentoring that I've learned? Well, the first is that you need to tailor mentoring to each individual's needs. No two individuals are alike. What motivates one person turns another one off. So you have to really tailor the mentoring to each one's needs, and those needs change throughout their period of training. So you really need to get to know your students and fellows very well, because the better that you know them, the more you can tailor things to their individual needs. Very important, encourage focus. I always tell people in my laboratory that there are four keys to success in research. The first is focus, the second is focus, the third is focus, and the fourth, well, that you have to figure out for yourself. I'm often reminded of an old beat-up microscope that I used to use when I was in medical school. I remember sitting in my dormitory room with the oil immersion lens, studying slides for histology or pathology. And it was a really old microscope. And every time I would turn my head away to look at the atlas to see what I was supposed to be looking at, by the time I came back, the stage would have slipped and it was out of focus. So I learned how to keep just enough pressure on the fine-tuning knob so that the stage wouldn't slip, and so that when I moved my head back to the scope, I could see things in focus. I subsequently realized that I played much the same role in my laboratory, because when I would go out of town for a week and come back and try to catch up with my students, I'd often find that they had lost their focus and headed off in some crazy direction or another based on an unexpected finding. So, of course, there are times when you do need to chase down an unexpected finding, but often it's just a distraction. And learning how to keep your focus in the face of such distractions is very important. Fan the flames of enthusiasm. Be enthusiastic about what you're doing. If you're not, find something else to do. When new people come to the lab, I always tell them, there are two conditions that are necessary, but not sufficient for you to succeed here. First, you're enthusiastic about your project. Second, I'm enthusiastic about your project. One of my excellent postdoctoral fellows, now a named professor at Cornell, told me a story not that many years ago, that when he was in the laboratory, he was convinced that his project was absolutely the most important one to me, the lab chief, because I was so enthusiastic about it whenever he discussed his data with me. And so he was mentioning this when he was in the lab to one of his lab mates one night, and the lab mate said, well, wait a minute, no, I'm convinced that Bob thinks my project is by far the most exciting, because he pretty much indicates that to me whenever we talk. And then a third guy piped up, no. He said, he thinks my project is the most exciting one. So the question is, which of them was right? And of course, the answer is they were all right, because in the moment I would talk to them about their projects, I was so enthusiastic that they naturally concluded that their project was the most important one to me. Teach trainees to build their careers around problems, not techniques. We all know that all techniques, all scientific techniques, are ultimately replaced by newer and better techniques. So that if you build your entire career around a set of techniques that you learned when you were in training, and you never grow beyond those, you'll have a short career indeed, because every 15 years or so, technologies are completely redone by new discoveries, new technical discoveries. Promote risk-taking. Be bold, take risks, and don't be afraid to fail. Failure is a crucial part of success. If you talk to almost anybody who's been successful at any walk of life, they will tell you stories, and I already have told you some of mine. They will tell you stories about the extraordinary amount of failure that they experienced early in their careers. So you can't be afraid to fail. In fact, you really need to almost embrace failure as a way of learning what works and what doesn't work, and how you can learn from failure and build better and better experiments. Model dogged persistence. There are problems, scientific problems, that I have worked on for not even years, but a decade or more before we finally crack them. So you really need to sort of settle in for the long haul. Empower trainees. Now, this is one of the most important jobs of a mentor, and it involves walking a very, very fine line. Here's what I mean. On the one hand, if you micromanage the trainee, if you tell them everything what to do, design the experiments for them, even when they eventually succeed, they lack the confidence of knowing that they were responsible for the success with your coaching. Instead, if you have overmanaged them, micromanaged them, they will conclude that it was really the boss, the mentor, who was responsible for the ultimate success. They will lack the intellectual ownership and confidence that comes from knowing that they have cracked the problem. So very important not to micromanage. On the other hand, if you're too distant, then they get nothing from you. And they might as well not be in your laboratory. So you have to learn where the line is, and it's different, as I mentioned before, it's different for every trainee, and for any given trainee, it's different depending on how far along they are in their training. So the ability to empower trainees by giving them just enough guidance to keep them on the straight path, while at the same time allowing them to really own the project themselves, is perhaps the most important thing we have to do. Emphasize storytelling. Learn to tell a good story. You know, I learned this lesson actually in my clinical life, but it really turns out to apply perhaps not just as well, but even better to the research world. So when I was a young medical student, my very first clinical rotation I took was at Mount Sinai Hospital in New York City. And I, on the very first day, was asked to present a case to the attending physician, which I did. And we discussed the diagnosis and the differential diagnosis. And then he said to me, okay, Mr. Lefkowitz, now I want you to represent that case. You cannot change any of the facts of the case. You can't change any of the clinical data. But I want you to tell me a different story. Well, I was stumped. I had no idea what he was talking about. So then he asked some of the other students. They were equally nonplussed. Then he went around the room, interns, residents. Nobody could do anything. He said, well, let me demonstrate. And so he did. He didn't change any of the facts. He used all the same data. But by emphasizing different facts, by putting them in a different order, he came up with a rather different story. And in fact, it led him to a different differential diagnosis and ultimately to the correct diagnosis, which my presentation had not done. Well, the lesson he was teaching was that data are not a story. A story is something you impose with your own creativity on the data. And of course, this is exactly what we do in science all the time. So when we are getting ready to write a paper, we'll take the various figure panels that we might be using, and we'll put them in different orders, move them around, much like that attending physician was doing with the clinical case. So we have the data, but not the story. And so learning to tell a good story will stand you in good stead, whether you are talking about clinical medicine or a research project in a paper. Laugh and have fun. Try to see the humor in everyday situations. If you have the right attitude, it's all around you. I find that humor is a great prod to creativity, and I try to leaven my lab and other meetings with a generous amount. In fact, when you think about it, humor is a very creative enterprise. It involves some of the very same things that we do in science. It's a matter of looking at some things and seeing relationships that others might not see. In fact, something that's funny is generally the experience you have when you are able to put together some things that don't seem to go together, that normally wouldn't be juxtaposed, and all of a sudden in a flash show a relationship between them which reveals sort of the humor. It's sort of in the moment that you see the joke that somebody is telling, you're making a small discovery in seeing a relationship that you didn't previously see. And of course, that is the core of scientific discovery, putting things together that others may not have done, seeing relationships that others may not have seen. Plus, it's a lot of fun to laugh. And I find that in my lab meetings, the more I get people laughing and having a good time and relaxing, the more the creative ideas flow. And respect your own mentors. I'm fortunate in that the mentors that I had so many years ago at the NIH are still alive, and believe it or not, both are active. One is 89, the other one is 90, and they both still have laboratories and still are working. One is still at the NIH, Ira Paston. The other left there long ago. His name is Jesse Roth. A few other keys to success. Do lots of experiments. Among the trainees I've had who were the most successful, a fairly general characteristic has been that they did more experiments than the average trainee. Don't talk yourself out of experiments too easily. Even if you have numerous reasons why an experiment won't work, consider doing it anyway. Often you'll be surprised at the result. Be ambitious. Nothing wrong with ambition. You have to really want to be successful in order to be successful. Try to view your work as play. I must say that, of course, like anybody else, there are days when I may have to do some things that seem like drudgery, administrative tasks, other things, committee work. But by and large, I can say that for the most part, the laboratory has always been my sandbox. It's where I feel like I am playing and not like I am working. Be optimistic, always very important, but easier for some than others, depending on your personality. And something I always drill into my trainees: preparation, preparation, and more preparation. Whether it's giving a talk, writing a paper, preparing for an examination, you can't prepare enough. And I model that in my own behavior. Now, in the last part of my talk, I just want to, on a lighter note, talk about some of the amazing people and experiences that I've had, both before and after the Nobel Prize. I mean, winning a Nobel Prize, there's no doubt, changes your life forever. I talked before about the remarkable group of people that I met at the NIH, 10 of us winning the Nobel Prize. But that was just the tip of the iceberg. The people who came to the NIH in that program went on to essentially form my entire generation of professors in medical school and deans, etc. In my class, if you will, at the NIH from 1968 to 70, those we had graduated medical school in 66, there were 4 future Nobel laureates in that class. Myself, Mike Brown and Joe Goldstein, work on the LDL receptor, and Harold Varmus, discoverer of proto-oncogenes. But also in our class, not a future Nobel laureate, but more famous than any of us will ever be, is a gentleman shown here, Tony Fauci. So that's me and Tony. Many years later, in the 90s, we're good friends, have been ever since the NIH, and I've been in touch with him on a number of occasions since the pandemic started. Another classical example of the talent that came out of that program. I've gotten to meet several presidents, George Bush, who presented me with the National Medal of Science a few years before I got the Nobel. Of course, I met the King of Sweden when I received the Nobel Prize in 2012. I met President Obama when I won the Nobel Prize. It turned out that it's a long-standing tradition going back, I think, 60 years for the American president to meet with all American Nobel laureates when they are on their way to Stockholm in December to receive their prizes. So there were 5 of us, 5 Americans in my year, and with our spouses, we were invited to the Oval Office to meet with President Obama. It was a wonderful experience. He was just so natural and amusing, and he has this wonderful self-deprecating sense of humor. And as you may recall, in his first year as president, he received the Nobel Prize in peace, which turned a few heads because he really hadn't had a chance to do much that early in his presidency. But so he was kidding around with us, and he said to us, I really relate to you folks. He says, because as you know, like you, I too am a Nobel laureate. He says, but there's one key difference. He says, you earned yours. So that got a good laugh. I'll point out to you that President Trump did not continue this long-standing tradition of meeting with the Nobel laureates. And in fact, during his 4 years in office, he never met with a single American Nobel laureate. I got to meet the famous coach Mike Krzyzewski, the Duke basketball coach. He was he's the winningest coach in the history of NCAA men's basketball, over 1,000 games. I'm an avid fan of the Duke basketball team, go to all their games, but of course I had never met personally with the coach. I was a great admirer of his. The day after I got the call from Stockholm, he called me up on the phone. We had a lovely conversation. He said to me, Bob, he says, I really relate to what you've done because, I brought Duke our very first NCAA sports championship. And now you've brought the university our very first Nobel Prize. So I want you to come down to Cameron Indoor Stadium. That's the basketball arena next week, and we're going to honor you. And so I did. And as you can see, they brought me to center court team, and they presented me with a jersey with the number 1 on it. And of course, that was a huge thrill. And you can see the students in the background with their hands in the air, and they're sort of chanting and just really going crazy. And I could hear they were chanting something, the students, but I couldn't quite understand what it was. But then it came into focus, and I could see they were pointing at me like this, and in unison they were chanting, "He's so smart, he's so smart." And of course, at that point, I put my arms in the air, and it was just an amazing thing. So that was, and I got a big hug from the coach. So that was another amazing thing. There's me in my office with my jersey hanging from the ceiling, and on the other side of me, my Nobel medal and Nobel certificate. One last little story. Something that Nobel laureates get invited to do from time to time, and I'm no exception, is to throw out the first pitch at a baseball game. Now, we don't have a major league team anywhere near Durham, but we do have a AAA minor league team, the Durham Bulls. And so I was invited to throw out the first pitch at a game the summer after I won the prize. Fortunately, I was given a couple of months warning, so I had some time to practice. Now, when I was a young man, I used to play a lot of ball, but it had been many decades since I had thrown a baseball. And the first time I tried, I could see that I had a long way to come. I couldn't even throw the ball 60 feet anymore. And when I did manage to throw it 60 feet, I was completely wild. So I started practicing. And for 2 months, I would practice with anybody who would play catch with me. Particularly helpful was my granddaughter in San Francisco, who was the pitcher on her high school team. She taught me some important things. Then as things got closer, the last week before the big day, I called up the Duke men's varsity coach of the baseball team, and he sent the pitching coach to the field with me, and he worked with me so I would learn to throw off a mound, not just on the flat. And so I felt I was ready. And so then the big day arrived, and of course you have only one shot at this. So if it goes badly, there's nothing you can do about it, and it'd be very embarrassing. Meanwhile, the trainees in my lab kept sending me links to videos of things like worst 10 first pitches ever thrown, in which people would throw the ball sideways or trip and fall off the mound as they threw the ball, etc. So that didn't really help my confidence. But anyway, here I am on the big day. From the left, that's Wool E. Bull, the team mascot, myself, Victor Zhao, at the time the CEO of Duke Medical Center, and Mr. William Bell holding the microphone, who was the longtime mayor of Durham. So the big day arrives, and now it's time to see if I'm going to be able to do it. So I'm going to show you a little video. It's very hard to follow where the ball is, but I encourage you to just watch where the catcher catches the ball. So that's me, as you'll see, walking out to the mound. See the Jumbotron in the background. Okay, here we go. Big wind up, and boom, right there, it catches it waist high, perfect strike. And so then came one of the proudest moments of my life. The catcher walked out to the mound and to give me the game ball, and he slapped it into my mitt, looked me in the eye, and said, quote, "Doc, that was one hell of a throw." And I must say that was one of the proudest moments of my life, to tell you the honest to God truth. This is a picture of me. I'm not going to tell you what the circumstances of it were. If you're interested, you'll need to get a copy of my book. This is a picture of me with two aging rock stars. To your right, that's Sting, and to the left, Peter Gabriel. And as I said, if you're wondering what in the world are these two aging rockers doing, kneeling in front of Dr. Lefkowitz, looking up at him so admiringly, well, if you want to know about that, you'll have to read the stories in my book, where you'll find many other stories. So the last slide I want to show you is here. And this is especially for the young people or anybody else in the audience who may themselves aspire to win a Nobel Prize. Many Nobel laureates have written or made videos about their advice or tips for winning a Nobel Prize, and they have a variety of ideas about this. I've got my own, and it's based on personal experience, and this article, which appeared in the prestigious New England Journal of Medicine. Now, this article was entitled Chocolate Consumption, Cognitive Function, and Nobel Laureates. And interestingly, this actually appeared in the issue of October 10th, 2012, the day I got the call from Stockholm. I did not become aware of this article for almost another year when it was pointed out to me. Now, what it purports to show, I suspect somewhat tongue-in-cheek, is the following. Along the x-axis is plotted chocolate consumption per individual, per capita, per year in different countries. And on the ordinate scale is the number of Nobel laureates per 10 million population. You can see that there's a direct and highly significant correlation. Each country is represented by their country's flag. You can see that there's really only one outlier, and that's Sweden, that seems to be getting more prizes than they deserve based on their chocolate consumption, which of course raises the question of whether they're showing any favoritism to their own scientists. But so why do I show this? Well, I've been a devotee of dark chocolate for essentially my entire adult life. And for decades, I had been eating 2 small squares of dark chocolate, usually about 75% cocoa, maybe a couple of nights a week. But the summer before I won the prize in 2012, I said to my wife, look, I'm almost 70 years old, and I love dark chocolate. My cholesterol numbers are very good. I'm doing really well. My weight is good. Why do I limit myself to chocolate 2 nights a week? I think I'm going to start eating it every night. She says, you should. You deserve it. And so I did. Sometime in July or August of 2012, I began eating dark chocolate every night. And 2 months later, I won the Nobel Prize. Now, what can we conclude from that? Well, I think there are a couple of things. The first is that there's obviously a threshold effect. It's dose-related, and you need to get above a certain threshold of chocolate, which obviously is greater than 2 times a week. But perhaps even more importantly is the fact that it's obviously very rapidly acting, because within 2 months of increasing my dose of chocolate, I won the Nobel Prize. So for all those aspiring Nobel laureates out there, let me heartily recommend dark chocolate. Let me conclude by again mentioning this new memoir that I published just a few months ago. If you enjoyed any of my stories, you'll find many, many more in here, some funny, some serious, a chapter on mentoring, chapter on my science, all sorts of interesting things. But I think it's a good read, and I think you'll very much enjoy it. And so on that note, I'm going to end and stop sharing my screen. Thank you very much.
Okay, thank you very much for your lecture, Professor Lefkowitz. It was great to hear a little bit about your science, about your career path, and there were very many fascinating stories in there, such as the yellow berets, that many of us were probably not aware of. And what you talked to us about can serve as an inspiration, not just for scientists, but I think for any professional in any fields. And on a personal note, as a Swiss native, of course, I fully condone your last statement on the chocolate. I agree with that 100%. I now ask our panelists to come up here, please. that after the lecture we can start the panel discussion. We will have four discussion points. We'll talk a little bit about the science of GPCR receptors and what's still left to do. We'll talk about what motivates scientists. We'll have one topic on what the current topics might be in life science that are worth pursuing. And then one that's very near and dear to us here at the Institute for Basic Science, talk about the importance and impact of basic research. So again, our panelists here to my left, Professor Xu, Professor Che, and Professor Myung. Welcome all of you. And as we said, at the end of the panel discussion, we'll have an opportunity for all of you to ask some questions. So let's start with the first discussion topic, a bit of science on the GPCR receptors. So Professor Robert Lefkowitz was awarded the Nobel Prize in 2012 for his discovery of the GCPR receptors and G protein-mediated signal transduction. As he pointed out in his lecture, the importance of these receptors is evident from the fact that an estimated 30 to 40% of drug targets actually target these GPCR receptors. And me, like many others, teach it in, I think it's the 5th class in the Biology 101, so it's really profound knowledge. So that the topics that I wanted to discuss a little bit here is we know so much about these receptors, so what are still some of the areas that are underexplored or need to be addressed in GPCR receptors, both worldwide, and then maybe our panel can weigh in on what the status is on that research in Korea. What are the important research questions, and also what are the impacts of this research for academia, economics, and society as a whole. So Professor Lefkowitz, maybe you can get us started. What are your thoughts on these topics?
Yes, I think there are currently several really important directions that research in this field is proceeding. One, there's been an explosion of structural work. Prior to 2007, there were no structures, atomic level structures of G protein coupled receptors. But then Brian Kobilka, my former student and co-Nobel laureate, broke the field open when he published the very first crystal structure of the beta adrenergic receptor. Since that time, roughly 15 years ago now, the field has exploded. And due to developments in crystallography and cryo-electron microscopy, every week structures are appearing, not just of the receptors, but the receptors in complex with their signal transducers. And it's not just one signal transducer. So the canonical signal transducer, which gives the receptors their name, were the G proteins, the heterotrimeric G proteins, hence the term G protein coupled receptors. But again, I didn't go into the science during my talk, but we discovered another molecule, or small family of molecules, called the beta arrestins, which we discovered around 30 years ago as molecules which were responsible for the phenomenon of desensitization. That is to say, the fact, almost universal amongst GPCRs, that even in the face of continuing stimulation, their signaling wanes over time. That's called desensitization. And we showed that this was due to phosphorylation of the receptors, followed by binding of beta arrestins, which block signal transduction through the G protein by sort of getting in the way of the G protein. Well, then we discovered subsequently that these beta arrestins, even as they were shutting down G protein signaling, could signal in their own right. They were alternate signal transducers. And then it turned out that there are some drugs that are able to signal through either G proteins and not arrestins, or the other way around. We call these biased ligands. And so I think one of the big areas right now, and one with tremendous import for drug discovery, is trying to find ligands which can stimulate signaling through either G proteins or arrestins, one with not the other. I'll give you an example. The reason this is important, because it turns out that sometimes the desired therapeutic effect that you want is being mediated through one of the transducers, whereas some of the side effects, adverse effects, being mediated through the other. For example, consider opiates. We know we have an opiate addiction crisis in the United States. Well, it turns out that the pain relieving effects of opiates, and they are the most powerful pain relievers that we have, the pain relieving effects are mediated through G protein signaling. But the side effects, constipation, potentially lethal respiratory depression, tolerance, these are all mediated through Berestin-mediated signaling. So if you had what we call a G protein biased ligand for the mu opioid receptor, which is a classical G protein coupled receptor, if you had a G biased ligand, you should have a drug which would be just as effective in pain relief, but which would have fewer side effects. And just such a drug has been developed and is FDA approved in the United States within the last year, and that's the first biased ligand. And there are many other examples. Essentially, any receptor potentially could show this kind of bias. So I think in terms of drug development, this is a very important area. So that's one. But related to that is all this structural work that's going on, because it allows the design of compounds by essentially using structure-based drug discovery, so that you can actually do virtual docking of structures of small molecules into the known structure of receptors to try to find new ligands. So that's one whole area. Another one is so-called allosteric ligands. So to date, virtually all of the 700 ligands for the G protein coupled receptors, except for 2 out of the 700, are what we call orthosteric ligands. Now, orthosteric ligands are ligands which bind, drugs which bind to the orthosteric site of a receptor. So the orthosteric site of one of these receptors is the site, highly conserved, where the endogenous physiological ligand bind. It's where adrenaline binds to an adrenergic receptor. It's where histamine binds to a histamine receptor, where serotonin binds to a serotonin receptor. As I said, these are very highly conserved sites. For example, there are 15 different serotonin receptor subtypes, but they all bind serotonin, which means the evolutionary pressure to keep that orthosteric site highly conserved is great. And hence it's very, very difficult to design drugs which are going to be receptor subtype specific. But allosteric ligands are ligands which bind anywhere else on the receptor. And what we're learning is that these receptors are virtually decorated with all sorts of sites that we didn't know about, which of course are much less highly conserved and therefore allow much greater specificity from one receptor subtype to another. So I think another big push in drug development over the next decades is going to be the discovery of allosteric receptor drugs. And again, I don't have time to go into it. There are all kinds of new methods for doing this, some of which are based on structural work, some not. The final area I would highlight is that, you know, the classical concept which we taught for years was that signaling from G protein coupled receptors always originated at the plasma membrane. But now it's been shown by a number of groups that the receptors not only can signal from the plasma membrane, but that as they're internalized, they can continue to signal from inside the cell, from endosomes. And in fact, the consequences of that signaling from inside the cell are completely different from the signaling that occurs at the plasma membrane. So those are just a few of many areas that I could highlight that I think are really hot areas right now.
Thank you very much. Looks like you still have a lot of work ahead of you. That's great to hear. Professor Che, maybe you've been working on these GPCR receptors. Maybe you wanted to add something. Also, maybe how it relates to research done here in Korea.
Yeah, I think in Korea, unfortunately, especially in the structural biology field, GPCR research is a little bit far from reaching the top level. Well, there'll be some reasons, but probably one of them is not that many structural biologists are working on the membrane protein. including GPCR, because it's hard. It takes more time to get the result, and also the infrastructure is not well being equipped, unfortunately, in Korea yet. As Dr. Lefkowitz mentioned, the cryo-EM and X-ray crystallography really boost up the structural study of GPCR, but currently there are only 2 Titan cryos in Korea available. Well, hopefully next year we'll have 4 more. So I think GPCR research will be activated in the near future. I would like to actually ask Dr. Lefkowitz about, he actually mentioned the really important things, not just the endogenous ligand. He mentioned the allosteric ligand and bias ligand, which can be applied to the new drug development. And Dr. Lefkowitz, how do you think the basic science outcome can be connected to the development of drugs and use in the pharmaceutical companies and so on?
So, you know, it's interesting. In my laboratory, the primary focus is not, nor has it ever been, on developing drugs ourselves. We try to understand basic principles of biology with respect to the receptors, and then pretty much leave it to others to leverage those discoveries to develop new drugs. But we have, over the course of the past 5 years or so, discovered several allosteric drugs for example, the beta-adrenergic receptor, which actually have potential as actual drug candidates. But the fact is that we are not directly interested in using them as drugs. We rather use them as tool compounds because we're very interested in biophysical questions, such as the different conformations that the receptors may assume when occupied by different types of drugs. So these compounds, these allosteric compounds, for example, that we may seek in the laboratory to gain new tools to study the biophysical and conformational properties of the receptors, can also do double duty or additional service as clinical drug candidates.
One thing maybe I wanted to ask you about and emphasize is the development of cryo-EM, which of course has been a revolution in all of structural biology, larger complexes. And how important do you think it has been for the GPCR receptors in particular?
I think it's been transformational. It's completely transformed the field. 15 years ago, when Kobilka published the first atomic level structure of the receptor, which was followed over the next 5 or 8 years by numerous structures, not just by him, but by many other laboratories. They were all X-ray crystallography. And then the cryo-EM juggernaut began. And all of a sudden, everybody was publishing cryo-EM structures. Now, you mentioned infrastructure. To set up a cryo-EM facility with state-of-the-art equipment and everything that goes with it costs about $10 million. And then it costs probably $1 million to $1.5 million to run it per year. So you got to have a lot of money to do this. But to give you an example of the power of the technology, after Kobilka published a crystal structure of the beta-2-adrenergic receptor in complex with GS, the heterotrimeric G protein, in 2011, neither he, that was 10 years ago, neither he nor anybody else was able to get another crystal structure of any other receptor with any other G protein. And that went on for years. And then about probably 4 or 5 years ago, people started publishing cryo-EM structures of the receptor in complex with G proteins. And now there are many dozens of such structures, all by cryo-EM, none by crystallography. And the same is true of receptors in complex with beta-arrestins. There are now a number of published structures, a couple from my lab, of receptors in complex with beta-arrestins. But again, all by cryo-EM. So the short answer to your question is it's been absolutely transformational in the structural biology of GPCRs.
Mm-hmm. Thank you for your comment. And good for everybody in Korea and IBS to take note. It's certainly true for many fields. Professor Xu, maybe we can have your view on the field and anything you'd like to add.
Long time no see. Okay, I really enjoyed your talk. Okay, so I think it will be great time for young Korean scientists to have opportunity to hear how you have arrived as scientists until established your own research field. Well, so number of research on cell signaling, including GPCR study, is relatively large in Korea. According to National Research Foundation of Korea, out of 18,000 projects, about 4%, about 8 projects, and it's cell signaling, and 15% of them, so about 100 projects, is GPCR project. Meanwhile, the latest research trend on signaling in Korea are the same as the global trend, such as the study on molecular mechanisms, signaling, on the structure analysis, deophanizing, in vivo validation, GPCR-based drug developments. Okay, so I'm enjoyed, again, your talks.
Okay. Thank you very much. Maybe we can move on to the next topic, and that is sort of, what motivates you to be a scientist over a long time. So in your case, Professor Lefkowitz, you've been doing this for many years, 50 plus years, and so many of us are wondering, what is it that keeps you going still after all the success you've enjoyed?
That's a wonderful question. Obviously, there's no external motivator or incentive. It comes from inside. There's like an engine inside that drives me. Ever since I was a little boy, I wanted to do something that mattered. And I wanted to use whatever talents I had to accomplish something. So in that sense, you could say I was driven. And so it didn't matter how much success I had. It was always in my mind a matter of what's next, what's the next question. And one of the wonderful things in science is that if you pick a good problem to begin with, then every answer that you get immediately poses new questions to answer. Right. And when you answer those, it poses new ones that you couldn't previously have even known were questions. It's the old business, it sounds trite, but it's true, that when you finally climb a mountain, you're able to see the next mountain range, which you couldn't see before. And when you climb that mountain range, now you can see the next one. And it's kind of interesting. I was reflecting on this the other day that, as you said, my career is over 50 years now. But it's true that if you could take any experiment going on in my laboratory today, and you could ask, well, what was the basis, the genesis for that particular experiment? And you would identify an experiment we did a couple of days ago, and then you could say, well, what was the basis for that experiment? And it was an experiment we did the day before that, or a week before that. And you could keep tracing it back, and you would get to the first day I opened my laboratory in a essentially unbroken chain. So it's always been a matter of putting one foot in front of the other, and somehow the thing just seems to stay very interesting. And of course, as we all know, the main driver of scientific research is curiosity. I'm a curious person. I just always want to know how things work. My intention from the beginning was to just figure out things that I was curious about. I wasn't specifically thinking about trying to develop a drug or something like that. And yet, as we've talked about, our work laid the basis for about a third of all the drugs used in the world today. Especially for some of the young people who may be listening, you don't have to directly do clinical research to have to come up with findings that can tremendously impact the practice of medicine.
We'll get back to the point of the importance of basic research toward the end. And one thing that you said that certainly resonates with me is that the complexity that continues to increase in all of our research fields. So when I look at our own research fields, it seemed very simple when I was a graduate student. And it gets more and more complex, so whenever you solve a problem, there's the next one. But it's also what keeps us in business, so that's a good thing. And we learn more about how life works. Professor Myung, maybe you wanted to add to this topic. What is your motivation as a scientist? What drives you? What do you enjoy about doing it?
Yeah, so even though I don't get the Nobel Prize yet, I hope for, but and then talk to the Nobel laureates, it's a kind of a little too junior. Is actually talking about how I become a scientist. But for me, what I chose as science is a relatively very different from Bob, because so my parents always want to become a doctor, medical doctor, and like my brother. And then I really hate it, actually, that seeing patients every day is the last thing that I want to do. So that's the reason I chose a science instead. And so that's my first core, I guess. And then I got a very good mentors, actually. I had so good mentors during graduate school in Korea as well as in the United States. Even when I was in NIH as an independent investigator, I had very great mentors. He nurtures almost every day. So that helps me a lot. So that's probably keep me doing science as a business. And then plus, and I have a very good trainees. And they input me, actually. Whenever I actually turn down something, they encourage me to going back and challenge that. So I learn a lot, actually, from trainee too. So I can say that having good mentor, having good trainee, that means people around you. That's the motivation that I keep my science so far.
Very good. Professor Che, what's your experience?
Well, I was actually lucky to work with Brian Kobylka when I was at Stanford University. He actually showed enthusiasm in GPCR structural study, and I actually learned a lot from him. That I think I'm really grateful. I'm also trying to keep, as Dr. Lefkowitz mentioned, I try to keep having good questions to answer those questions. And so I think as Dr. Myung mentioned, I had good mentors and also had a good training at Stanford University, and that's how I working on GPCR structural study in Korea. Yeah.
Very good.
You know, if you studied with Dr. Kobylka, that makes you my scientific granddaughter.
Okay, so anyway, when I started study in graduate school, I thought that in order to understanding living organs, it was necessary to elucidate the identity of molecules involved in physiological functions. With this, in this mind, phosphoinositide specific phospholipase enzymes, one of key enzymes for signal transductions, was isolated and purified, and several genes of phospholipase isozymes clones. Since then, I have been studying phospholipase-mediated signaling, so which have identity one by one through roles of phospholipase isozyme, like monks. Okay.
All right. Thank you very much. So maybe we can talk about the next topic and the different research fields. And so I think this is particularly relevant for us here at the Institute for Basic Science. We also always look to push the boundaries and identify and foster the really important, addressing the really important questions today in science. So I was wondering from our panel, apart from the signal transduction and the GCPR receptors that we already talked about, what in your mind are some of the other most important current developments in the life sciences? Professor Lefkowitz.
Well, I mean, that's a very broad question, and obviously a matter of personal taste, to say the least. I think I find some of the most fascinating questions to be those in neurobiology.
Agreed.
We seem, despite all the work that's gone on in trying to understand brain function, we seem to be so far still from any really deep understanding of what it means in physiological terms to think and to have consciousness. And I know that's a problem which has engaged some of the finest minds in science over the years. But there are some huge communal endeavors going on where people are mapping connections in the brain, and they're making these atlases of brain wiring connections, etc. And then a variety of new technologies have come about in order to study brain function. So I think that neurobiology and the quest to understand how the nervous system works at a cellular and molecular level is certainly one of the key areas.
Mm-hmm. So how far do you think, in terms of neurobiology, you could argue at some point it's also signal transduction. So how far is it away from the level of understanding you've achieved in your research? How far away are we from this level of understanding in neurobiology?
Yeah, I think that it's an interesting question. I think in terms of understanding the signaling, it's at the same level. But the problem is in terms of understanding how you get from the signaling, at the molecular level, to the higher level organization of different neural networks and how they function, to actually think and send messages over longer distances in a coordinated way. I think that's where the blocks currently lie.
Mm-hmm. Mm-hmm. All right, very good. That's certainly one important area. Maybe we'll go back the other way. Professor Xu,
so absolutely
any areas you think we should
so
consider?
agree with you. So now it is possible to study brain research, especially in signal transactions, molecular interactions. That's why, cryo-EM, like cryo-EMs, now imaging technology is well developed, So this technology can make unknown brain functions be possible. So that's why I moved to Institute of Korean Brain Research. Okay.
Professor Che?
As a structural biologist, I actually working on the structural study of GPCR, so mostly like in vitro studies. But currently there are some other techniques called cryo electron tomograph, cryo-ET. I actually would like to ask Dr. Lefkowitz, so we actually want to see the endogenous receptor in the physiological condition, not the overexpression system. Do you think we can actually see in the near future how those receptors are working at the plasma membrane or going into the signalism formation, something like that in physiological condition? That's actually, I think it's a kind of important question, but I don't know how far we can go.
I also don't know, and I don't know if the cryo-electron tomography will take us there, but you raise an extraordinarily important question because for years, decades now, most of the research in GPCR signaling is done in overexpressed systems. So when you overexpress receptors and transducers, when you overexpress them in cells, you create systems which don't exist physiologically. And so whenever you do that, the normal physiological specificity of things breaks down. I mean, if you're expressing a receptor at 10-fold its normal concentration, and that would be modest overexpression. Typically, when people are overexpressing things, it's at least 10, if not 50-fold above normal. So let's say you're overexpressing a receptor 10 or 20-fold above its normal levels, and now you're overexpressing another protein which it might interact with, such as a G protein or a beta-arrestin, also at 10-fold. So now you have the product of the two is over 100. Well, if you're trying to investigate the specificity of how this receptor works, well, you can't do it. I mean, because you'll see interactions occurring which quite possibly never occur physiologically because the concentrations of the reactants are just not high enough. And yet this is the way almost all signaling research has been done because there has been no other way to do it. When I first started my career, in the early years before anything was cloned, we were forced to work at endogenous levels. And, it was working at endogenous levels of these proteins that led my lab and Gilman and Rodbell, Krebs, to work out the original sort of principles that we still use today to understand signaling. All of that was done before anything was cloned. But then, since things have been cloned, as I say, now it's so easy to just overexpress things to study them. But the problem, as you very correctly point out, is that that's not a physiological situation.
Maybe Professor Myung, do you have any areas we haven't discussed yet that you think are critical?
Yeah, so Orlando, as you know, that for me, DNA is the best thing to study. So the genetic information stored in DNA. But besides my field, what I think is, I totally agree with the neuroscience, but one more thing that I can say is that developmental biology. We still don't understand early development, how that can be. That fast time, those are very, very little time or period that we can make an entire organism. And not just a human. If you think about all those small fishes, less than 3 days, they make everything. And that's wonderful from just a single cell. And still we don't understand. So that's a wonderful study that the young people can challenge. I think I'm too old actually to tackle those, but we are trying, but that's definitely the exciting field that young people can jump in.
Okay. Maybe I'll bring up one more point, and that's perhaps a little counterpoint to one that you made, Professor Lefkowitz. You said, and that's the way I operate too, we should work on a problem rather than a method, right? Mm-hmm. However, a counterpoint to that would be that in the past, always, but particularly in the past 15, 20 years, the way science has been transformed by technology is tremendous. So one is computing power, that we can analyze things. The other is the power of sequencing, where we can analyze enormous amounts of data and make good use of it or not. At the structural biology level, in addition to cryo-EM, it's computational prediction, just as AlphaFold and RosettaFold, to do that. And then also all the imaging and mapping we can do at a whole cell level that has given us sort of access to perhaps problems we didn't even think of before, or didn't think that we could address them before. So I wondered if you had any thoughts on your view of these technological developments in recent years.
Well, yeah, I'm glad you brought that up, because if you took from my remarks that I did not think it was worthwhile to work on technology development, then
that's not what I meant.
Yeah. Okay. Yeah. Because that's certainly not the point I was making.
Yep.
In fact, I think the history of science shows, and particularly in the G protein coupled receptor field, that in order to make real breakthroughs in any field, somebody's got to develop new technology. And I know I spent the first 10, 15 years of my career developing one new technology after another. When we started out, there was no way to study the receptors. So we developed radioligand binding techniques. And then there was no way to isolate them. So we developed affinity chromatography techniques. And then there was no way to purify them. So in addition to affinity chromatography techniques, we had to develop all sorts of photoaffinity and affinity probes, which didn't exist. So in order to make breakthroughs, you invariably have to develop new technologies. My point was just that whatever technologies you've developed, they're going to be replaced in 15 years, either with technologies that you or somebody else developed. So if you tie yourself, I mean, look what's happened with X-ray crystallography. I mean, many of the X-ray crystallographers I know are using more cryo-EM today than they are the beamlines. So those that have not acquainted themselves with the techniques of cryo-EM or don't have access to the facilities are being left behind, even though they may be wonderful structural biologists. So I think that's just a good example of that.
Yeah, good. All right, so maybe this can bring us to our last topic on basic science. And while we do this, I encourage everybody in the audience, either in person or online, please get your questions ready. We'll be looking forward to discuss them in 10, 15 minutes. So as we all know, the Institute for Basic Science in Korea was founded on the premise to promote basic research. And we certainly heard in your talk, Professor Lefkowitz, also the importance of basic science and how it's played in your area and how that basic knowledge has then led to very broad applications. So my question to you is, can you tell us a bit what Duke University does to foster basic science? And maybe do you have any initiatives in the United States that you think are particularly productive in promoting basic science?
Yeah, I think that the key thing is that a university be committed to the value of basic research. Our medical school is particularly fortunate in that the clinical enterprise at Duke University Medical Center it makes a lot of money. It's a big business and a very successful business. And some percentage of the annual profit, I don't know what it is basically goes directly to the medical school, which then distributes it to the various basic science and other research departments. So that's a very important way. The other thing is there's a huge initiative going on at Duke right now to further enhance the basic research enterprise through recruitment of outstanding basic scientists at every level of seniority, all the way from assistant professors to full professors. So I think there isn't a specific thing that they're doing as much as just generally stressing the importance of basic research to the university mission. And that they have put a lot of emphasis on computing power and data, large data sets, etc. So those are some of the things that are going on at Duke.
I mean, having previously worked at a U.S. medical school in the United States myself, there's always a struggle between the clinical research, where the income is, and the basic research, where the interesting discoveries lie. And so maybe do you have any advice or lessons from your career how you managed to convince people in the medical school to invest in the basic research, or for Duke University to keep making that a priority?
Yep, what you say is certainly very true, and Duke is a leading institution in clinical research. We have something called the DCRI, which is the Duke Clinical Research Institute, which is really world famous for running large clinical trials. So we really run the gamut from very, very basic research to clinical research. I think that one of the ways that I have been able to promote basic research at Duke is that when people look at, my long career at Duke and the fact that I was always doing very fundamental, very basic molecular and biochemical research, and yet all these drugs came from it, really caught the attention of the deans and people who run the place, and brought their attention to focus on the fact that, as I've been saying during our session tonight, that even the most fundamental research can yield very, very important clues to how to develop drugs and make clinical advances. So I think that it was in recognition of that, and I'm not unique at Duke in those regards. I mean, I was the first Nobel laureate at Duke, as I mentioned, but then Paul Modrich, a colleague of mine in biochemistry, 3 years later won the prize in chemistry for his work on DNA damage repair. Again, Paul is not a physician. He's a very basic molecular biologist and biochemist, and yet his research on mechanisms of DNA damage repair has huge implications for understanding the basis for and the treatment of cancers. So again, I think the people at Duke came to understand that. But you're right, there often is this tension between the clinical departments and the clinical research and the fundamental research. And at Duke, like at other institutions, I mean, the basic research departments have no way of generating money,
the revenue,
other than grants. They have no revenue, whereas the clinical department, surgery, medicine, pediatrics, whatever, they have huge revenues that come in. So it's up to the dean to make those distributions, and they do. And basically, they take the money from the clinical departments, and they say so much of this is going to go to basic research. Mm-hmm. But yeah, you have to have enlightened leaders who are willing to do that.
Mm-hmm. And so maybe a follow-up question, a little different. You mentioned that you have a lot of the clinical trials going on at Duke and a big division in that regard. Has that helped you in your basic research, maybe having these interactions with people conducting clinical trials?
Well, I think it has. Not me so much, but I have many other colleagues who are in, if not basic research, what would be called translational research.
Right.
And as a result of all these large clinical studies that go on, they have these huge banks of blood samples and tissue samples and biopsy samples. So when somebody develops some new technique or approach, they go to the people who in the Duke Clinical Research Institute, and they say, well, we're studying this new molecular abnormality that occurs in such and such a disease. Do you have any relevant samples? And they say, oh yeah, we have 300 samples from patients who had that disease. We didn't know what to do with them, but we have them, in the freezer. Mm-hmm. So yes, although that has not really been anything that influenced my own work, I have many, many colleagues who have profited from such things.
All right, thank you. So maybe we can focus discussion a little bit also on what your views are in this in Korea. In Korea, we also have a lot of applied research, right? Korea is very famous for applied research. And so we're very grateful for IBS, and it's kind of what brought me here to come to Korea to help establish the sort of more basic research areas. So maybe we can hear from our panel what, in your institutions, what is done for your basic research.
Yes. So, recently, even though science research has been elucidated through the various types of collaboration rather than one disciplinary basis. Okay, so in other words, I think that is multidisciplinary collaboration research should be done for effective progresses. Okay, therefore, in my institute, our institutes encouraged, group and multidisciplinary study. So around one themes. Okay.
Mm-hmm. Yes. Professor Che?
Yeah, our university, SNU, actually encourages, especially for young PIs, to do their own research. not working together with their previous PIs as an independent investigators. So our university has a creative pioneering researchers program for young PI, which actually supports some amount of money for 3 years to maximum 9 years. I think that really helped a lot, I think, especially for me, with the support of the program, I could start the GPCR structural study. Yeah.
Good to hear. Professor Myung, maybe you can comment on IBS's mission in this regard and how you feel IBS is doing.
Yeah, IBS is wonderful. Yeah, without IBS, how can I be here, right? So you know, like Bob, as you know, that we actually established this wonderful institute in Korea that can actually promote basic science. And I totally agree that all those clinical applications is important. The reason why I'm saying this is when I was in NIH in the US, one of my friends at the Bob Nussbaum told me that this interesting story. That just a regular person asked him, who are you working for? Who are you working for? And then his answer is, I'm working for you because I got research money from your taxpayer. So I was very impressed actually with that. And so we IBS, we work for you. We work for all the people who pay taxpayers. And that's probably the same in the US. And therefore, we need to bring up something that can promote basic science, that can help our existence as a basic research. So I think even though we do fundamental basic science, very, very fundamental, however, we need to show this can lead to your concern or your question to all those people. That's what we can survive as a basic scientist. And then that's, I think, very important to do.
I think one of the things that's important for us to emphasize to people is that you know the value of basic science only often in retrospect in a broader context, right? Some of the things we do are wildly successful, for example, the work on GPCR receptors, and other endeavors maybe not quite be as successful, but at the outset we don't know which ones are going to be the groundbreaking ones. And so I think this is something we have to make people understand. And there's lots of anecdotes and stories about science. CRISPR, Cas9, genome engineering is one of them in recent times that really have come from very basic curiosity-driven research. And so we all agree that this is very important. Very good. So maybe now we can have a couple of questions from the audience, either here, starting with the people here in the auditorium. If you have any questions, please raise your hand. You can ask about anything you want to ask to the science or to broader topics, being a scientist, to any of us here, or Professor Lefkowitz. Oh, there's a chat question here. Okay, so here's a question from the chat. We can start with that. How do you envision the future of crystallography? Theoretical, computational, structural biochemistry is growing. So should this field be invested more than cryo-EM?
Well, I'm afraid that's beyond my competence to answer. I'm not a structural biologist myself, so I'd rather not comment on that.
Maybe I would say that they all go hand in hand. So one thing that cryo-EM can do is look at the dynamic structure of large complexes in different assemblies. When we have the theoretical calculations such as AlphaFold, it can give us the basic structures of protein in a really quick time and also maybe look at some of the interactions. So in my view, all of those go hand in hand, and it depends on the problem that's being addressed. Professor Che, you're a structural biologist, or Professor Lefkowitz?
Yeah, I was just going to say that it's worth bearing in mind that when we're talking about the biophysics of these signaling systems, that X-ray crystallography and cryo-EM are static techniques. They give us a photograph of one conformation, okay? But the systems we're studying are extraordinarily dynamic. I mean, the whole basis for this phenomenon of biased agonism that I was talking about before, we presumed even before we had the data, we presumed was due to the fact that different ligands could stabilize different active conformations of the receptor. But those conformations generally cannot be investigated very well by either cryo or crystallography unless you have other tools to stabilize a conformation. I mean, Kobilka showed this right at the beginning. He could take the beta-adrenergic receptor and put the strongest agonist that he had on the receptor, okay, even a covalent agonist on the receptor, and he still got a completely inactive structure. The only way to get the active structure was to have the agonist on there, but then to have another tool to stabilize or lock the receptor in that active conformation, which turned out to be a form of antibody called an antibody. So to get some of these dynamic pieces of information, one has to turn to other techniques, such as spectroscopic techniques, electron paramagnetic resonance, or NMR, DEAR, double electron resonance, which is an EPR technique. These techniques complement what you get from the crystallography and cryo. The crystallography and cryo are sort of like taking a snapshot of a galloping horse. You catch it in one conformation or another. But with some of these other techniques, you can actually like make a movie, in a sense, of different conformations. Right. So they all go together.
Right. There's also additional areas. For example, one can make chemical tools, reactive probes that can probe a receptor, or mass spectrometry together with cross-linking is a technique that comes to mind that is very frequently used, that combines very well with these other areas. All right, do we have any other questions from the audience here or online? Any questions are very welcome. Anything you have curious to ask scientists is very welcome. Just go ahead, don't be shy. Ask whatever you always wanted to ask. Yes.
Thank you very much, Professor Lefkowitz. I'm the president of IBS, and I would like to ask, you are the first Nobel laureate in Duke University, and people there must be proud of you, and they must be proud of themselves. And we are still waiting the first Nobel laureate in Korea and also at IBS. So what kind of a research environment should we provide? Or is there anything as an institute can do to promote those, other than providing, dark chocolate?
Well, dark chocolate is a good start. But I do have another idea. So I was aware of the fact that Korea has never had a science Nobel laureate. The reason I know this is that during Nobel Week back in 2012, in December, when I was in Stockholm to receive my prize, they had a whole series of events, and we were having a question and answer period, and I was on a panel, and a Korean journalist stood up and mentioned the fact that Korea had never had a science winner of a Nobel Prize. He asked me if I had any ideas for what might be done to change that situation. And at the time, I didn't have much of a good answer, but it really started me thinking about that over the subsequent months and even years. And here's something that did occur to me. I thought about the fact that when it comes to sports, let's say you have a country that has one of the most outstanding Olympic teams in whatever, track and field, fencing, ski jumping, whatever, hockey. What you'll find is that these countries have programs that start when kids are very, very young, and they start culling the very best, kids in terms of whatever the sport is. And as they progress through and as they get older, they go from one elite sports camp to another, and then, to preparation for the Olympics, etc. And so eventually, by the time they get to be adults or young adults, there's been this process going on where the best of the best are sort of being progressively picked out by various objective criteria and groomed for these teams. And so the question is, could you do this in science as well? And I realized in the United States, we do exactly that. I mean, the Bronx High School of Science. So the Bronx High School of Science, I'm the 8th Nobel laureate to graduate from the Bronx High School of Science. Think about that. This is one high school that's existed for about 75 or 80 years. And they've graduated 8 future Nobel laureates. I'm the 8th. So think about that for a minute. If the Bronx High School of Science were a country instead of a high school, it would rank about 20th in the world. So there are only about something like 19 countries that have more Nobel Prizes than this one high school. So how's that possible? Well, because they got the very brightest kids to go there. And then those very bright kids, go on to other institutions which are picking out the best of the best. And then during the Vietnam War, they were further picked out to go into this Yellow Beret program that I was in, etc. So I wonder, I don't know anything about the educational system in Korea, but I think if you want to get those Nobel laureates, I think by the time they get to the career stage where they're taking jobs at an institute, that's not the place to start. I think you have to start with very young people and give them opportunities, and then have ways of picking out the most innately gifted and talented and move them into special classes with their peers where they can be challenged and stimulated by other kids who are just as bright and just as driven, etc. That's something to think about.
Mm-hmm. Maybe if I can speak for a little bit as an observer, having lived in Korea for a couple of years, one thing I noticed, and also when teaching the students here, they're very motivated, very bright, and a lot of them study extremely hard during the high school years, and a lot of emphasis is on getting the right grades to get into your favorite college. And maybe having a bit of focus away from the grades and on softer skills like one does in the US, that you have laboratory research experience or play the violin or these types of things to make your career. I think maybe start that mindset earlier on, I think will be useful. I observed that students that are freshmen, they're still locked into that grade mentality, but as they progress through their studies, I think that changes, and maybe having that change start earlier on would also be a good thing.
So I can add one more thing, that as Bob pointed out, that what I noticed from the Korean students, it was that they are afraid of the failure. So that failure really actually hardened and then make a progress. Yeah. But what I noticed in recent Korean undergraduate students, they're really afraid of the failing. Mm-hmm. They only want to have a perfect score, perfect something. But that's not really become a scientist or even other jobs. You need to get through this bitter failures.
Do you think this is a question of society too? For example, in the US, you can start 10 companies and they all fail. If your 11th is a success, you're golden, right? And I think in Korea, this is maybe a bit more challenging to sort of embrace that failure and say, well, you learned something in the process, here's your next chance.
And that's probably the truth, because what I learned, even though my kids were not grown here, so I did not clearly say it, but so many of my cousins, they were educated to get the perfect score. So that's a real challenge. Actually, you don't. You can fail. And even some things you cannot solve, and then you get challenged from there. But that's not the case nowadays.
I give a talk at Duke about once every year or two to all the research fellows in the basic science departments. I give a talk entitled "How to Deal with Failure and Rejection in Research." And yeah, I mean, failure is so important, and one really has to get. The other thing that I think there are some societal differences from one culture to another is to really make scientific breakthroughs. You have to be willing to question everything, whatever the accepted wisdom is, whatever the paradigms are, whatever it says in the textbooks. You have to be willing from time to time to say, well, not so fast. I don't know if I believe that. And I have found, I've had a number of Korean students and fellows, and some of them seem less willing to do that. They are, for example, and this I understand, they're not willing to challenge me, whereas some of my American students really are. I mean, and hey, I have no infinite wisdom. Sometimes knowing too much, knowing all the right answers can actually be a hindrance, because in a sense, if you kind of know all the facts, it's kind of harder to really challenge things. I used to somewhat tongue-in-cheek tell my students that the secret to my success is how little I actually know. So I'm willing to question almost anything. So that's worth bearing in mind, I think.
Mm-hmm. I think we have one more question from a Zoom participant, if I could see that on the screen here.
Yes, hello.
This is Katrin Gluck, who happens to be working in my laboratory. Thank you for joining us, Katrin. Please ask your question.
Yes, hello, Dr. Lefkowitz. Thank you for that very inspiring talk. As Professor Scherer already said, I am a graduate student in his lab at IBS in UNIST in Ulsan. And I wanted to ask you what you think are the challenges for graduate students in medical research nowadays that might be different from when you were doing your first research, or maybe even just differences to 15 years ago, and how we can overcome them.
Well, it's interesting. I think one of the biggest challenges is really a social challenge rather than a scientific challenge. And it has to do with the fact that it wasn't 15 or 20 years ago when I was at your stage. It was more like 50 or 60 years ago. And in those days, families usually had one provider, typically the male, and one domestic partner, typically the female. And the female was generally at home raising children and taking care of the household. And the male was out, pursuing a career. But over the years, fortunately, that stereotype changed, and virtually all couples today consist of two, usually co-equal breadwinners, if I can use that expression. Now, amongst scientists, they most often wind up marrying other scientists. Of course, because who do you meet, right? I mean, you meet people at work and, in the laboratory. So now you have two careers, and now you have all the challenges that go with the two equal careers and having a family and doing all the difficult and time-consuming work and balancing, well, where are you going to get a job? I mean, this one wants to go to this city, this one wants to go to that city because it's a better opportunity. So I think your question was, what's different in the way of challenges? To me, that's one of the biggest challenges. How do you balance life and scientific work in this kind of environment? People often ask me that, and I always tell them, you're talking to the wrong guy. I mean, I didn't, all those years ago really have that issue, but I counsel so many young couples and people on that score these days that I'm continuously reminded of just the challenges.
Thank you. Thank you, Katrin. Do we have any more questions? If not, I think we can start to come to an end here. I thought this was a really informative discussion. I hope all the participants benefited from the discussions we had and found some inspiration in it, particularly from Professor Lefkowitz's remarks and presentation, and then all the discussion. Finally, I would like to thank everybody here at IBS who made this event possible and organized it. Some of you can see it, but it feels like we're in a TV studio here on, I don't know, Colbert Report or something of that sort. So it was a pleasure to do that. And Professor Lefkowitz, thank you very much again for taking the time to join us. I really enjoyed this, and I thought it was very inspiring. And so my name again is Orlando Scher. It's really my pleasure to host this event for you. So thank you all for joining. And let me ask you all to please, for a last round of applause for Professor Lefkowitz for joining us today. Thank you very much.
Thank you. Thank you.
Picture, yes.